This video is going to be about drawing Lewis structures. I'm going to try to keep these short, so we'll start off with simple binary compounds and look at the basics of drawing Lewis structures. We'll start with molecules in which the central atom is from period 2. So for example, let's look at a molecule like BH3, which is called borane, right? So when we're drawing a Lewis structure, the first thing we have to do is draw a connected structure. So one thing we find is that hydrogen, since it can only form one bond, can never be the central atom. So in this case, right, we can put the boron in the center and the hydrogens attached to it. Right? So the first thing you do is draw a connected structure. Then we'll add up the available valence electrons. Right? And so the available valence electrons, right? Boron has 3 valence electrons. Each hydrogen has 1 valence electrons. And so we've got a total of 6 valence electrons to account for in our structure. Well, each bond is 2 electrons. So each line we've already drawn is 2. Right? So we've already accounted for all 6 valence electrons. We have no electrons left, and so we're done, right? And so that structure is the appropriate Lewis structure for borane. So there's a simple beginning. So now let's consider another molecule, CF4, or carbon tetrafluoride. Okay? Now in this case, we're deciding what goes in the center, right? In this case, it's usually the less electronegative atom that is in the center. That is carbon in this case. So we're going to draw a connected structure. We'll put carbon in the middle. Fluorines around the outside. Right? Now we're going to add up our valence electrons. Right? Carbon has 4. We've got 4 fluorines. That's going to be 4 times the 7 that each fluorine has. So we're going to have 4, and we're going to have 28. That gives us a total of 32 valence electrons. Right? We've got 1, 2, there we go, 3, 4 bonds already drawn, each of which is 2 electrons. That's 8 electrons already accounted for. So we subtract those 8 because we already know where they are. Leaves us with 24. And so now we start distributing those 24 around the atoms starting from the outside in. So we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. And so now we're out of electrons. Each atom there has 8 electrons around it, and so that is the appropriate Lewis structure, right? Lewis structures include not only bonds, but also unshared electrons. And I prefer X's for unshared electrons. Some people prefer dots, and I prefer that electrons be shown individually. And so that is the appropriate Lewis structure for carbon tetrafluoride. Okay? So we put the least electronegative atom in the center. We add up our valence electrons. We subtract our bonds. We find out how many are left. We distribute them from outside in until we're out. Okay? So that's another straightforward one to begin with. Our next molecule we'll consider is an unusual one we don't see very often, but it is oxygen difluoride. Now, this is one of the few cases where there's something more electronegative than oxygen. So we have oxygen has to be in the center, which puts fluorine on the outside. So there is our initial connected structure, right? And so now we're going to add up our valence electrons, right? Oxygen has 6. The 2 fluorines, that's 2. Each fluorine has 7. So that's 6. That's 14. Gives us a total of 20. Right? We've got 2 bonds, right? 1 bond there, 1 bond there. Each bond we've drawn already represents the position of 2 electrons. So that's 4, leaves us with 16. So we start distributing our leftover electrons to give outside atoms 8 and move in. So we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And so now then, right, we put 12 there, still leaves us with 4. Those have to go on the central oxygen, right? Minus those 4 leaves us with 0. And if we look now, right, every atom has 8 electrons around it. 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. That's the goal. And so this is an appropriate Lewis structure, right, showing both bonds and unshared pairs, or unshared electrons in pairs if it's possible, right, around the molecular structure, right? So that's dealing with simple molecules where we have period 2 atoms in the center, okay? And so